This is lesson 2.5 for pre-calculus. This is about transformations of functions, and we did a little bit of review of this in Unit 1. We're going to go into more depth now. So I want to recall the transformation of a parabola, a squaring function, where we have y equals x squared. If we're going to transform it, instead of being the parent function, y equals x squared, we have these different things that we can do to manipulate it. We can multiply the squaring part of it by a. We can subtract from our input this h. Now it's always subtracting. It's always x minus this h. And then outside of the squaring function, we can add some other amount, k. And we need to talk about what each part of that refers to. So in this transformation of y equals x squared, the h is the horizontal change. It's how we shift it. So it's called a horizontal shift. The k is a vertical shift. The a, if it's positive or negative, describes the opening. If it's a positive a, it's opening upward. If it's a negative a, it's opening downward. What that's also referring to is if our a is negative, you're going to reflect over the x-axis. If it's positive, we just do it going upward. Now, forget that it's positive or negative. We'll just look at the absolute value of it. When that number, a, is greater than 1, then it is a horizontal stretch. It gets skinny. It's like you're pulling the top little pieces here. You're holding it down here and you're pulling it, and it stretches it to become skinnier. If my absolute value of a is less than 1, then you are, actually it's called a vertical compression. It's like I always say it's like an elephant sat on the parabola and it squished it out. Okay? So that would be a vertical stretch or a vertical compression. Shifts, reflect, stretch or compress. Okay? Now, we can do the same thing to any function. We would still have out here whether or not it is a positive, like the parent function. If it's a negative, it's going to have reflected it across the x-axis. If the a absolute value is greater than 1, it would have stretched the function vertically. If the a is between 0 and 1, or the absolute value of it is between 0 and 1, then it will compress. It'll look more squat. We have a horizontal shift and a vertical shift. The f is the name of the function, the parent function that we have memorized. We have absolute value function, so it could look like this. We have exponential function, so it could look like that. We have a power function. Now, make sure that you know the difference between exponential function and a power function. Power function is like saying a quadratic or a cubic and things like that. Exponential function is when we have a base. Okay. The root, like a square root or a cube root or any kind of root, we have same thing. We can have transformations of any of those functions. The symbols are used by convention. This a, the h, the k, all that. That's not like a law, but we do use those symbols. Okay? So many times we just say f of x minus h for horizontal shift. But in calculus, we don't use h because, again, h is just a convention that we get used to. Once you get to calculus, we don't say h and k or any of that. We pretty much use c for all these things because these are not variables. They're a constant. They're a constant we don't know. When you're first learning it, I'm pretty sure that these letters came from something to help us remember. H for horizontal, K for vertical. They don't want to use V, so vertical, so K is the kind of sound for that. And so that's where those came from. But in calculus, we'd just be using C. And it just means when you have x minus c, you're going to move to the right c units. When you have x plus c, you're going to use to the left. Okay. When we add at the end, that's going to be going up or down. So we have c is for the constant. And just because it's a letter doesn't mean it's a variable. Remember that. Variable is the thing that changes. It's like the input. All the other letters and symbols we see have other meanings, and they're not variables. Negative f, negate the function versus negating the input. These do different things. When you negate the function, the negative on the outside of the function, that negative a, that's where it's going to reflect across the x-axis. It's going to, like as if you folded on the x-axis, and whatever was above goes down below, whatever was below goes above. When we negate the input, we now reflect over the y-axis. Now there's also a difference between multiplying the outside of the function versus multiplying the input. We talked about this a few minutes ago when we talked about the a and said, oh, when you have an a out here, it's either a vertical stretch or a compression, but it's vertical. It's as if you're taking your hands and pulling up and down, or you're up for stretch, or you're smushing it down for compress. But when you're multiplying your x, that's not a vertical stretch or compression. That is a horizontal stretch or compression. So now it's as if we're taking the ends this way and pulling them out, and it's going to make it wider. Or we're taking our fingers and we're squishing them in, and when you squish it in, it compresses it and makes it go up and makes it look skinnier. So again, this action here is a vertical compression. This is a horizontal stretch. Both of these make it look wider, but we're doing different things to the function. The vertical is always to multiply the function. Horizontal is always to multiply the input. And it does have a difference in what it does to the function itself. So let's look at that. Whenever we're doing vertical, meaning we are multiplying the outside of the function, the zeros will always remain the same. When we stretch it, it'll go higher up when it's maximums. It'll go down lower when it's minimum, and it will start looking very elongated. When it's a compression, well, that C is between 0 and 1. It gets closer and closer and closer to the x-axis. It gets, it flattens it. But our zeros remain the same, even though we've multiplied it. What happens when we do a horizontal stretch or compression? Well, when we do a horizontal stretch or compression, when we pull it to the left and right, do a horizontal stretch, and it gets wider, it changes our zeros. Our zeros are no longer in the same place. But what doesn't change is our relative max and our relative mins. Our relative maximums and our relative minimums stay the same height. So it is very different in how it affects our function. The next topic we want to talk about is odd and even. And if we look at it graphically, what's happening graphically with odds and evens? An even function means it has y-axis symmetry. I always talk about that this is like the butterfly effect. So when you fold the paper on the y-axis, the left side and the right side will land exactly on top of each other. And that's y-axis symmetry. Not just vertical symmetry, it has to be y-axis symmetry. And then we know we have an even function. Now again, this is if we're looking at the graph, not if we're looking at the equation for the function. So let's look at that, how we figure it out when we don't have a graph. Let's say I did not have this graph, and I couldn't see that it has this y-axis symmetry. If my function, I know it, I plug in a positive 2, I plug in a negative 2, and I compare their outputs. When their outputs are exactly the same, it will be an even function. Okay? Right. So when you have the same outputs, you've got an even function. An odd function, when you're looking at the graphs, this is different. If we folded it on the y-axis, the left side does not land on the right side. Instead of folding, what we want to do is we want to spin or rotate. So we're going to take this positive y-axis and we're going to rotate it 180 degrees till it comes down here. Meaning you're going to take the paper, and what was the top is now going to be at the bottom. And if I could do that here, I can't do that on my iPad here. But if I could do that, if I flip this 180 degrees around, it would look exactly the same. You wouldn't notice a change in this graph. The same thing here. If I did flip this around 180 degrees, it would look exactly the same. That's called rotational symmetry. It's actually rotational symmetry about the origin. It has to be around this origin here, the 0, 0. What does it mean algebraically? Well, algebraically, it means this. Again, if we didn't have the function to look at, if we see this function, we can see it. But let's pretend we don't have the function to look at. We just have equation. We take the equation of our function and we plug in a negative. We also take that same function, we plug in a positive. So plug in a -2, plug in a +2, and compare the outputs. Now again, if they were the same, well, that would be even, and we're talking about odd now. If we do this, plug in opposites, the outputs, where I have a positive f here and a negative f here, that means we get opposite outputs. So another way to look at that is I plug in a -2, I plug in a +2, I get some output, let's say it's n. Then I do this to the other one, and I get the opposite. I get the -n. That means I've got an odd function. So this is algebraically. When we look at the graph, that's graphically. So if every term in a polynomial is of even degree, every single term, this has a 4th degree, this has a 2nd degree, this has a 0 degree. Remember, 5 is like 5x to the 0. Every single variable in this expression, I shouldn't say every single term has an x, and every single x is an even degree. Since every single x is an even degree, then this is an even function. Now, that's not the definition of even function. That's a byproduct of it. It just happens to be that if all the degrees are even, then it itself is even. And it also works the same thing with polynomials. And each term, if every single term is odd, I have x to the 7th, x to the 5th, x to the 3rd, x to the 1st. All of those are odd. If I had a constant, then it wouldn't be odd, because I'd have, like if it said +5, that would mean +5 times x to the 0, which is considered even. So that wouldn't be odd. But this has all odd degree terms, therefore it is an odd function. Mixed degrees are neither. That's the thing. Functions can be odd, even, or neither. Now, again, that's not the definition. The definition is you plug in opposites and you get the same value. That's even. You plug in opposites and you get opposite outputs. That's odd. That's the definition of even and odd. And that is the end of our lesson for today. Make sure you have your notes written down and that you post your notes to Google Classroom.